So now we have the hash, an array of buckets. The question is, which entry goes to which bucket? For instance, when we are putting a key value pair, which one of these buckets does it go in? And then when we are looking for that entry, which one of these buckets does the hash look for it? We don't have to do it. We don't have to deal with it as a developer from outside. The hash takes care of it all. That's its reason for being. But how does the hash know which entry is in which bucket? The answer to that is in the key object, and within it, the hash code of the key object. Which one of these buckets the key value pair will go in depends all and only the value the hash code of the key object returns. The value object has nothing to do with it, and the equals method of the key object has nothing to do with it at all. Equals is something that belongs in the business logic. It is a binary relationship between two objects, and it just tells from the business angle whether two objects are equal to you in the development, to the application. HashMap has no way of knowing, no way of telling whether the hash code and equals contract is holding just by looking at the value the hash codes and equals of a bunch of objects return. It just isn't mathematically, theoretically is possible, and it isn't any meaningful here. HashMap is just looking at the hash code of the key and deciding deterministically which bucket that specific entry is to go in. Here's how it does. It first shuffles the bits around a bit to break any possible patterns, because if the same or similar hash codes keep coming in, they all go into the same buckets or the same set of buckets. There'll be collisions, which isn't desirable. So hash code first shuffles the bits around in a deterministic way. It isn't just some random shuffling. This is what it does. We don't need to spend too much time on it. It's not relevant. It is in the hash method within HashMap. It is this hash method, I think, is, if I remember correctly, package private or private. It isn't public, but it is just as a note if you're interested to look it up. Just quickly, what this does is it keeps the high order 2 bytes as is. So an integer is 4 bytes. The first 2 bytes remain as is. And as for the second 2 bytes, it takes the exclusive OR of the first and second half, and that's it. Once it's done, all it does is look at the rightmost k bits in the outcome of this process, this calculation, and that's it. It just looks at the k bits, because k bits tells the range of values that can be represented in k bits is from 0 to 2 to k minus 1. Which is what HashMap is interested at this point, because it has 2 to k buckets. This is why HashMap keeps the size of the table always a power of 2. The bitwise operations are very easy. So let's put it all together in an operation, on the put operation. Let's see what happens behind the scenes when we put an entry, a key value pair, into the hash. So we have a hash. We are passing in a key and a value for that entry key value pair be put into that hash. The best way to look at it is as two phases of this operation. In the first, we are finding the bucket index. That's mapping the key object passed in, that turning it in to one of the numbers here, one of the indexes. And for that, we are calculating the hash, running that, invoking that hash function, hash method. And for this example, in this example, there are 16 cells. The table capacity, hash capacity is 16. That's 2 to the 4. Remember, always a power of 2. So looking at only the rightmost 4 bits will give us a number here, one of these here. In this specific case, we ran the hash, got this 32 bits. We take the value of the low end 4 bits, and that says 4. So the bucket we are looking for, the bucket that key should go in, the entry with that key should go in, is this bucket, the bucket at index 4. The computation time for this operation is constant. This calculation is constant, and reaching the bucket on the array is constant, direct memory access. No matter how many entries there are, this operation is constant. Only the hash code went into this operation. The hash code had the word on which index it would be. Equals had nothing to do with it. Once in the bucket, what needs to be done is to see whether this key value passed in is already there among the nodes there are in the bucket, if there are any. So for that, it has to search through these nodes to see the key values, whether they are equal to the one passed in. Now, for that comparison, it also uses the equals, business equality of the key objects, as well as the hash. It first checks hash, the hash on the node of this key, and the one passed in. If they check, if they are equal, then it makes sure that they are business equals also. So remember, we put the nodes into the buckets only by looking at their low order bits. Two nodes, even if they are of the same hash code, that doesn't mean that they'll be equals. But then this hash value is how the HashMap keeps track of its nodes internally. Especially in the case of a tree, a binary search tree keeps its entries ordered by a value to be able to provide the logarithmic access. And that value is the hash value here, value of the hash, calculated from the key, the hash code of the key object. So what it does is it looks for the hash of this key in the tree. If it finds a node with the same hash value, it then runs equals on the key, compares the two keys for business equality. If that checks also, then it found the entry. There already is such an entry in the hash. Then what it does is replaces this value object with the one passed in, and it's done. Returns the old value. If it couldn't find any such key, it then makes a new node, creates a new node with these fields on it, and inserts it to the tree or appends it to the linked list. This is where the equals comes in play for the very first time and never before. The computational complexity of the second phase is log n in the case of a tree. N here is the size of the tree. the number of entries in it. This log n, however, is not the last word on the computational complexity of the put operation itself. We'll have a lot more to say on that, but for now, we need this detail for our discussion on the poorly written hash codes, poorly overwritten, poorly implemented hash codes. The computational complexity of the put operation on a well-distributed hash is constant time. Let's take a quick look at the get operation as well. It's very similar to the put operation as to what HashMap does. It's its mentality behind the scenes. All right, let's quickly review it. So HashMap is being asked to get returned value corresponding to this key object passed in. So the first phase, it's again the two phases we are looking at it. First phase is exactly the same as put. It's finding, calculating it's seeing where the bucket is just by looking at the key. And then once in the key, it is the same search by the same condition, the equality of the key passed in and the keys in that bucket. It's first it's comparing the hash, and then if they are equal, it's checking for the business equality exactly the way it did in the put method. We'll now look into hashCode and equals contract. What happens when we break this contract? In the case of HashMap, this contract must hold on the objects of the key class. So what happens if we break it? What goes wrong where? Why? First, let's see what exactly this contract is, what it's saying. It's saying that for any two object pairs of the class, if those two objects are business equal to one another, then they definitely must have the exact same hash code. There's no other way about it. That's what it's saying, and that's all it is saying. Now let's experiment on hashCode and equals contract. We have a person class for that purpose. It will serve as the key type in our HashMap. It has one name field which tells the equality of the instances of the person class. Two objects of person are equal if they have the same name, if the same value is sitting in their name field. This equals is written according to that, so is the hash code. They are obeying the hashCode and equals contract. Everything is fine in this implementation. You can use your IDE for overriding hashCode and equals. I used Eclipse for this. I edited it a bit to save some space, but this is written hashCode and equals here are, especially this equals, it's pretty much the way Eclipse overridden for me. So in our code, in here, we have an Alice, we have a map, its keys are the person objects. We first put an entry, a key value pair. The key is Alice. We just put a value, the value of that Alice at that time. So at some point of time in our application, the value 1 comes up for Alice, and we put it into the hash. Let's run this first. So we put the value of 1 to the hash. Sometime later, sometime after, the value 2 came up for Alice, and so we want to update that, or you just invoke put again for the same key. At the second time, we didn't have the first Alice handy, the first Alice object as the key object. So we created some other Alice. Nothing wrong with that. All Alices are the same to us, by us, in our application. So the second Alice as the key is the exact same as the first Alice, which it is. The second time, Alice 2 found this first entry and replaced the value with the new value here. We invoked put twice, however, we only have one Alice in the hash. Now let's break the contract. Let's run it here. We now have our Alice and Alice2 are the same objects to us, to our application from that angle. However, they're not the same objects, they're not the same entries, they're not the same keys to the hash map. They have two different hash codes. We put the second time we put the object, Alice2, the key of hash code of Alice2 calculated to some other bucket, or even if it went to the same bucket, the hash values didn't check. It didn't see the first Alice at all. So it created a brand new Alice, a new entry with the same duplicate key. We now have two Alices. Everything is broken. To us, there's only one Alice. All Alices are equal, but that's not what the hash map says. Even some time after, so now here we updated the value of Alice with the one we had at this time, and then much later we wanted to get the value for Alice. We needed the value for Alice in our application. We didn't have either of these two Alices. We created another Alice and looked for it in the hash. We couldn't find anything. Although we have two Alices, we couldn't get anything for the very same key. Everything is broken. We have duplicate keys, and we are not finding our keys the way we should. This isn't a hash anymore. This is something else. This is only because we broke the hash code and equals contract. There's no other reason. I'll next talk about the overall HashMap performance, but before that, let's pin this down as well. This is a poorly overridden hash code. It's obeying the contract, nothing wrong with that. In fact, it couldn't be disobeying it because it's returning one specific value for all the objects there are. But then it's sending all the keys to the same bucket, one specific bucket. So all the keys, all the entries are placed in one bucket. They're all colliding. Because of this, it constantly returns. So it no longer is constant access, it's logarithmic. And even worse, if you're on Java 7, the tree structure in the buckets are since Java 8. So this is even worse prior to Java 8. It is worse than a tree structure because you're also burning a lot of memory space for nothing. Because what HashMap does is every time its size hits a certain threshold, we'll talk about these next, it increases its size, its length, the length of this table. It doubles it up. every time the number of entries hits a certain limit, it increases the size, but then it doesn't change anything. Everything is going into one bucket still. The rest of the buckets are all null. You allocated a lot of memory for nothing, and you have additional overhead for maintaining the hash structure. You're better off with a tree map here, the log n access. But then it depends on your application logic. Which data structure you'll be using is your application logic. That's what tells which data structures, and then you implement things right. You do the work on hashCode. This is just for the sake of the argument. So this is the extreme case. This is the worst hashCode there can be outside of disobeying the contract.